The first speaker is Federico Bonetti, and he will talk about aspects of categorical symmetries from Branes.
Thank you very much to the organizers for inviting me and giving me this opportunity to tell you something about this topic based on some recent works with my collaborators as listed there. Let me start with some very sort of broad introduction. Here, I have to admit I will be sort of guilty of using the language of global symmetries as related to topological operators inspired by that famous paper. And it's like a way of thinking about global symmetries in quantum field theory. And of course, one of the overarching questions that inspires and really motivates this whole workshop is to think about the interplay between global symmetries and gravity. And we already had many interesting talks about this. However, it is also like a very sort of broad question, and it's not so easy to discuss it. And therefore, for this talk, I would like to focus on something a little more specific and talk about some aspects of the problem. And in particular, in order to be definite, I would like to consider holographic settings inspired by top-down constructions in string theory or in M theory, in which, according to the duality, we have, on the one side, a non-gravitational field theory on some space-time, and on the other side, we find a theory of quantum gravity on a space with a boundary. And in this setting, the question that I would like to consider today, given that we would like to think about global symmetries on the non-gravitational side as being related to topological operators, what I would like to think about today, to consider today, is wondering how do we see the emergence of these topological symmetry operators if we think in terms of the gravitational side of this duality. And I would say that there is growing evidence that some non-trivial aspects of these non-symmetry structures that we have on the field theory side can be seen if we use Branes on the gravity side. And this point of view has attracted attention in the last couple of years. And here is like an incomplete list of some works, including many interesting contributions by many people in the audience. And again, for definiteness, today I would like to essentially restrict myself to finite symmetries. So I will not be discussing other like non-finite symmetries. And as I mentioned, one of the goals is to see to which extent we can use Branes to say something about the topological symmetry operators on the field theory side. And it turns out to be possible in many interesting examples. But what I would like to argue today is that actually we can do a little more, in that what we can see emerging from the gravitational side using Branes is essentially the structure of the SymTFT that governs the global symmetries of the field theory side. Which is to say that we see the global symmetry in question, but we can also see its 't anomalies in many situations. We have control over phenomena such as global variance of theories, or even more interestingly, things like generalized charges. And I will sort of introduce these concepts a little bit along the way. Indeed, for the rest of this talk, I would like first to say a few words about the SymTFT. So this section will be purely in field theory. There is no gravity here. And it's mostly so that we are sort of all on the same page to set a common language to use for the rest of the talk. As a reminder of sort of this, and also as a motivation of why the SymTFT can be an interesting object to consider. And after that, I will move to the sort of main point. Let's see. Namely, how do we see aspects of the SymTFT emerging from Branes? And finally, I have some brief conclusion. Okay, so before we consider, therefore, the problem on the gravity side, let's stick to just field theory and remind ourselves a little bit why we care about the SymTFT. And here is sort of a cartoon that I included to sort of convey the idea that we can think of it as an organizing tool or an organizing principle. It really allows us to connect in a way that, to me, it's quite effective, economical, several aspects of global generalized symmetries. They can be P-form symmetries or higher group symmetries. They may have anomalies. They may be responsible for different global variants. Here I mean something familiar, like maybe gauge theories that have the same gauge algebra but different gauge groups. And crucially, also some non-invertible and more categorical aspect of the world of symmetries. And the sort of key tenet of the SIMTFT point of view is that even if we want to study a theory that lives in D dimensions, we should look at something that lives in D+1 dimension. It's an auxiliary topological object that tells us something interesting about the symmetries. And in particular, here I would like to say a few words about what can be achieved with the SIMTFT. And there are also many more things that I don't have the chance to cover. First of all, I would say from a conceptual point of view, it's very nice because it's a proposal that allows us to disentangle, on the one hand, an abstract notion of symmetry, and on the other hand, the specific physical system on which we want to study that symmetry. So this is, in a sense, very similar. For instance, we are very used to the idea, the very useful idea, to have a separation in our minds between, for instance, an abstract group and the way it acts on a given physical system that we might be interested in studying. And this proposal is a way of achieving this in a world of generalized symmetries. And also on a more, if you wish, practical or computational point of view, the SIMTFT approach has been particularly fruitful for finite symmetries and crucially beyond group-level symmetries for various applications. For instance, it's a very useful tool to study multiplets or representations of categorical symmetries. And also, it gives us a way to access their anomalies in some interesting cases. And moreover, it has been used to really map out both gapless as well as gapped phases that have some symmetries. And here I'll just mention, but I will not be using it, there are actually proposals available to extend the SIMTFT picture to the realm of continuous symmetries. And actually, we have seen a brief appearance of it in Hotap talk for U1 symmetry, for instance. Okay, so let's briefly remind ourselves in pictures how this works. The main idea is to have this sort of famous sandwich. What we want to study is a theory in D dimensions. It's depicted here on the right. We realize it as an interval compactification of an auxiliary theory that has a topological bulk and has two boundaries. One boundary is gapped, it's topological, and we refer to it as the symmetry boundary. And the other side is not necessarily topological, and we think of that as the place where the physical degrees of freedom live. And here I'm emphasizing that while the bulk of the sandwich and the symmetry side are both topological, and they emphasize, in a sense, the abstract symmetry structure we want to study, the other side, as I mentioned, it's not necessarily topological and encodes the specific physical system that we want to study. And in this picture, say we want to realize a symmetry operator in our physical theory. Once the sandwich is open, it will be a topological operator on the symmetry boundary of this construction. Whereas, say we want to study something that is charged under a symmetry, so here it's depicted schematically by this red dot, but it doesn't have to be a local operator, it could be extended. Once we open the sandwich, it will be something stretched between the two sides. And intuitively, we can see that it's not going to be necessarily topological because it touches the physical boundary, and it will be charged under the symmetries because it touches the symmetry boundary, at least sort of heuristically. Yes?
So this physical boundary has some local action that's written on it, or it's all induced from the thing in the bulk?
No, it can be. The only requirement is that it can be coupled to the bulk. It can have its own degrees of freedom, its own action and dynamics. That's the generic case, I would say. Yes. Thank you. Okay. As an example, there are situations, for instance, when we care about finite abelian symmetries, maybe not the most exciting case, but definitely something we can consider, where we can have a Lagrangian description for the bulk TQFT. And roughly speaking, it's made of two kinds of terms. The first terms are BF-like terms, and in a sense, they are really the backbone of this topological theory. And the main idea that I would like to emphasize here is that we find pairs of fields with this sort of first-order topological action, and if we consider their holonomies on surfaces of the right dimension, this will link in non-trivial ways. There is a sort of a standard sort of Gauss link in the d plus one dimensional space-time that is captured by these terms. On the other hand, we could have more terms in the action that we can refer to as twist terms, borrowing the terminology of digraph-Witten theories. And here I would like to mention, even though I will not discuss it further, that these terms can also be thought of in terms of linking configurations, provided we adopt a different or higher notion of linking. And what I'm depicting here in this picture, to give you a flavor, is a sort of Borromean ring configuration. So those are three rings that, if you consider them sort of pairwise, they're really unlinked, but as a configuration of three objects as a whole, it does have some sort of non-trivial linking configuration. And this has been studied in various various works, including some recent ones. And essentially, it gives us a way, if you wish, of going back and forth between terms in a Lagrangian and a different point of view that is based more on having extended operators and their linkings in the bulk of the TQFT, of the SymTFT. And the linking is also a way of seeing how the action of topological operators on charged operators comes about in this way. For instance, we can imagine the situation depicted here in the top of the figure. Essentially, I'm just combining the two previous pictures. I'm realizing at the same time a charged object and some symmetry operator. And now we can imagine sliding the green topological operator, and there will be some linking in the bulk. We pick up a phase. But that's exactly what corresponds in the field theory, in the familiar statement that, at least for like a vanilla invertible symmetry, we pass the operator and we pick up a phase. But so why should we think about it this way? This might look a little bit like an overkill. The nice thing about this point of view is that it really allows us to discuss more general configurations, things that are often referred to as generalized charges. For instance, we can imagine a situation where when we slide this topological defect Q3 past this red Q2, something else is created. Another topological surface is generated. And once we close the sandwich, this corresponds to a situation where, here I'm depicting one example. Here I'm thinking to be in a 4D theory. There is some line operator and there is a zeroform symmetry defect. So we usually think that zeroforms should act on local operators, and they do, absolutely, but they can also act on lines. And in this instance, when this happens, on the other side, the line reemerges attached to a topological surface. So this is one example. And more generally, various works have shown that the SymTFT is a nice tool to think about representation theory for categorical symmetries. And finally, just very briefly, something we have already seen implicitly in some of the talks we had earlier, another couple of aspects in the world of generalized symmetries, I'm mentioning them because they will appear later. One is the notion of fusion rules. Essentially, it's a very natural idea that if we're looking at topological operators, we can sort of bring them together in a controlled and well-defined way and have something analogous, so to say, to an OPE. And while in the world of group-like symmetries, the fusion is relatively boring, it follows the group law. In general, we should consider more different options. In particular, we might have a sum or a linear combination of topological defects. And while this is not at all surprising, for instance, in 1+1 QFT, what has been realized recently, and now there are several reviews available, is that this structure is actually ubiquitous also in higher dimensional QFTs. So that was maybe not known explicitly or not expected, but has been established. And concurrently, it turns out that the essentially consistency of the formalism requires us to include also so-called condensation defects. This is also the idempotent completion that we saw earlier in Jacob's talk. And here I'm not going to really do justice to the mathematical underpinning of this concept. I'm going to use a very sort of simple-minded, intuitive picture of thinking of a condensation defect as a mesh, so to say, of lower dimensional defects embedded inside something bigger, which could be the identity defect, for example. And I mentioned these things because I would like to see, is there any way to reproduce this sort of structure from a holographic point of view? Okay. So if there are no questions about the general SimTFT review, I would like to switch gears and try to say something precisely on how we can see these sort of structures emerging. And in order to set the stage, I would like to start with a heuristic picture that can help us guide our intuition. So what I have in mind is a setup where we have, for instance, an ADS geometry in D+1 dimensions. And suppose we have control over its field theory dual, so that we sort of understand what is going on. And the standard holographic dictionary tells us that the gravitating degrees of freedom that live in the bulk of ADS are dual to the physical degrees of freedom that we have on the field theory side. And on the other hand, the expectation is that if we want to consider the symmetry aspects of the problem, we should look near the boundary, near the asymptotic boundary of ADS. So this is what brings us towards this heuristic picture in which what I'm suggesting is that the interior, so to say, of ADS, so where the modes that gravitate live, roughly speaking, we should think about it as being dual to the physical boundary of the sandwich picture, whereas the boundary at infinity gets mapped to the symmetry boundary. And in this heuristic picture, we can imagine considering a region of the bulk near the boundary. So if we approach that asymptotic boundary, and the idea is that essentially we work in a limit in which the topological aspects of the problem are the most relevant. And so it's this sort of small slice of the boundary, of the bulk, that gets mapped to the SimTFT bulk in the sandwich picture. So this is sort of the idea that I have in mind to try to guide my intuition and then try to say something a bit more concrete in concrete examples. And in particular, what many non-trivial examples have shown us in the last few years is that there is a picture in which we can consider branes that live in this gravitational theory and essentially have them approach the conformal boundary in a way that their non-topological aspects freeze out, but some of their non-trivial topological aspects do survive. And it is in this limit that we aim to extract robust topological features, such as linking configurations, or how these things act on one another, in such a way to learn that we can learn something about the symmetry structures on the field theory side. And here we have two basic configurations that it's useful to keep in mind. So on the one hand, I can consider a brane that lives entirely in a slice parallel to the asymptotic boundary, and I'm considering a limit where this sort of approaches the boundary. And this will become something that lives on top of the symmetry boundary in the sandwich, and it's going to be topological. Whereas, and this is something that we know from the older days of holography, we can consider suitable branes that sort of hit the boundary, go towards the boundary perpendicularly, and in that case, it's natural to expect them to be dual to these stretched operators, because essentially they sort of touch, in quotation, the symmetry boundary, they go all the way to infinity, but they are also deep in the bulk, which we think of as being dual to the physical boundary. So we have this picture. Very well. And actually, we can say something a little more concrete if we look at D-branes, for instance, the stable D-branes of type 2 string theory, because there we have a lot of information about their effective action. In particular, we know that if we consider a single brane, it will have a BBI action and non-trivial wet-to-mean topological couplings. And the remarks I would like to make here is that from the BBI action, we see that if we sort of embed this brane on a slice at some constant radius in an ADS or ADS asymptotic geometry, and we sort of imagine this being pushed towards the conformal boundary, the effective tension of this brane is going to scale like a positive power of this coordinate in coordinates where the boundary is at infinity. So this is telling us effectively why there is this freeze out of the modes on the brane. On the other hand, we see sort of clearly manifest the topological nature of the wet-to-mean coupling makes it clear that they remain non-trivial even if they take this limit. And here there are two things I would like to emphasize, well-known things. The first is the coupling to the bulk Ramond-Ramond potentials, and the second is the presence of a dynamical gauge field on the word volume of the brane. And we'll see that both these ingredients are important in the program that we would like to pursue. So the first, let me focus first on the coupling to the Ramond-Ramond fields. This is sort of well established, and here I'm just suggesting a way of doing computation. Like as a bookkeeping device, it's convenient to consider essentially the Bianchi identities for the Ramond-Ramond fields with sources. So here I'm depicting, for instance, one example of a Ramond-Ramond Bianchi identity. As you can see, I'm thinking of a democratic formulation where we have all the Ramond-Ramond fields. And for simplicity or convenience, I'm thinking of the branes as being magnetic sources. And this is essentially, we'll see a way that to consider how the coupling of the branes to the Ramond-Ramond fields translates into linking configurations. This might be a little abstract, so it's best, I believe, to consider a couple of examples. And as usual, let's start with the classic example of ADS5 times S5, dual to for D n equals 4 super Yang-Mills. And let's focus on the one-form center, the center symmetry, the one-form symmetry sector. In this case, the relevant branes on the gravitational sides are a D1 brane and a fundamental string. And I'm considering both to be points on the sphere, and they are extended at ADS. And if we adopt this point of view of considering them as they approach the conformal boundary, essentially all the non-topological features are washed away, and what they give us are holonomies of the C2 and B2 two forms that we have in 10D supergravity. And these two surface operators exhibit a non-trivial link in the bulk of ADS5. Of course, this comes as no surprise, and it's probably very well known to many, many of you. Here, the only thing I would like to mention is that there is a way of thinking about it precisely in terms of these Bianchi identities of sources. So, for instance, we can consider the effect of inserting a D1 and see what that means for that Bianchi identity, and then considering a ciphered surface for the support of the fundamental string, just a way of saying I'm assuming it to be the boundary of some sigma 3 prime. We can consider sort of an integrated version of that Bianchi identity, use the fact that we have n units of F5 flux in the ADS5 times S5 background, and say that the holonomy of B2, or the integral of H3 on sigma 3 prime, sorry, that was a typo, essentially gives us 1 over n times the linking number of these two surfaces. And clearly, we know that this is also encoded more simply in a 5-dimensional BF term. It's a famous coupling in the ADS5 effective action that reads like n times C2 dB2. And the case I'm considering here corresponds to choosing the Dirichlet boundary conditions for B2, because those are the ones that allow essentially the F1 to end perpendicularly and give us the Wilson line, whereas the D1 will stay parallel and it will give us the generator of the electric one-form symmetry of the SUN theory. And if you prefer to think about Branes and linkings, boundary conditions correspond to choosing a maximal set of operators that are sort of linking trivially, and they can all end on the symmetry boundary at the same time. And I won't be using this fact, but I'd like to mention that actually it has been shown in great detail that there is a one-to-one correspondence between the topological boundary conditions for this PF theory and the global variants of SUN theory that differ by their spectrum of line operators and global one-form symmetries. And now I would like to tackle another example in the same spirit, which is slightly more involved. And in particular, I would like to consider AES7 times RP4. We can think about it as the near horizon limit of a stack of M5 branes that we have put on top of a Z2 orbifold singularity. Sometimes it's referred to as an OM5 plane. And this is known to be dual to a 6D to 0 SCFT of type D, as opposed to type A, which would be the case of just a stack of branes probing flat space-time. You might be wondering why consider the D family? And I'm considering it here because it has some nice features that I would like to leverage. The first is that actually this CFT can be an absolute theory as opposed to a relative theory for any value of n. And I would like to remind you here that in contrast, if we try to do it for type A, like sort of algebra SUN, n should be a perfect square in order for the theory to be an absolute QFT. And here, absolute QFT essentially just means that we can consider it as is, whereas a relative theory only makes sense if we think about it as in this case, a gapless boundary of some other theory. But it's much more well-defined to study global symmetries of absolute QFT, so that's why I would like to consider this example. In particular, we'll see that there is a way of capturing finite symmetries of this absolute QFT from the gravity dual from AES7 times RP4. And there are two ingredients that make this computation, this check, interesting. And they are, on the one side, that RP4 topology allows for torsional cycles, which clearly are not present for S4. And at the same time, there is a non-zero G4 flux there. So there is an interplay of these ingredients, which might get a little technical, but I will try to give you an overview of sort of what sort of things we see. According to the paradigm I would like to sort of tell you about, we should look at branes in this geometry. And so the exercise becomes to essentially consider what the homology of RP4 is and select the cycles that can be wrapped by M2 and M5 branes. And we find 4 relevant objects. And the task is to consider their linking to begin with, and then maybe more sophisticated properties. Yes?
I have a bit of a naive question. Is there anything mysterious? Do you expect anything mysterious to happen to the SymPFD associated with absolute theory as opposed to relative ones? I just want to ask a bit more, like what's the motive? Some more about the motivation to study an absolute theory and the symmetries.
Well,
associated to
I would, because in the case of an absolute theory, the sandwich construction is much more well defined, and in particular the topological bulk in one dimension higher. It's truly just an auxiliary tool to study the symmetries of the theory that is already well defined in d dimensions. Whereas in the relative case, it's really non-optional, if you wish, to have the bulk in order to make sense of the theory. But one could also object that from a top-down point of view, it's actually very natural to have relative theories. That's what happens both in holography and in geometric engineering. But today I would like to stick to the canonical sandwich, so to say, and sort of that's why I'm choosing to focus on absolute.
So at the very least, I could say for absolute theory, the SymPFD is purely an auxiliary address because need not
Yeah,
be
exactly. Like the theory makes sense in d dimensions, and we don't have to have a bulk in one dimension higher.
Okay. Thank you.
Yes?
For the case of the relative theory, the topological boundary, you can just treat it as an interface, where there is something else on the other side.
Okay.
So you can still close, but then there is something left. So it's not.
Yes.
So the other side I can think of as trivial.
No, it's not trivial. It's an interface.
No,
It's
I'm asking
all
about
the same rules.
I'm asking about absolute theory.
In the absolute theory, the other side is the boundary. There is nothing on it's a boundary. Whereas in the for the relative theory, the the other side is an interface.
Okay. So just boundary conditions, let's say, maybe. Yeah, absolutely. Okay. Thanks.
Yes.
I probably missed this, but what makes the theory absolute in your supergravity description of the M5 wrapping this?
Yeah, I don't know if it's manifest from the supergravity description, but what I would like to argue in a couple of slides is that the low energy effective action in ADS7 has a bunch of topological terms. They're like, it's an abelian three-form Chern-Simons theory. The statement in that language becomes to see whether or not that theory admits topological boundary conditions. And the answer turns out to be yes for RP4, and the analogous question for S4, for general flux N, would be no. So that would tell us that it's a relative theory. Thanks. So, but here, sort of going a little bit ahead, because I'm anticipating that what I want to extract out of these branes is this linking configuration and the quadratic topological couplings that encode it. And here we see a new ingredient at play, which is really crucial for this to hold, and namely the phenomenon of non-commutativity of electric and magnetic fluxes on torsional cycles that we have in generalized Maxwell theory. And here I won't have the time to explain it carefully and do justice to it, but I can at least try to give you a flavor. So this phenomenon is usually described in a Hamiltonian setting. So here we're doing like a slicing of ADS, where the radial direction is Euclidean time in the Hamiltonian evolution. So we effectively consider a 10-dimensional space, which is some slice of ADS and RP4. I'm leaving RP4 as is. And there we have branes, for instance, an M2 an M2 and an M5 that one is on a sort of a point on RP4, the other is on an RP3. And the analysis of non-commuting fluxes tells us, in the language of branes, that the operators that these branes realize on these slides don't quite commute, but have this sort of commutation relation where a phase originates, which is computed by the so-called linking pairing of torsional cycles. And here the observation is that we can, if you wish, dimensionally reduce this linking pairing, exploiting the fact that our Tandy slice is a direct product of M6 and RP4, and essentially this object itself splits into a vanilla intersection number of cycles on the 6D slice, and a smaller linking pairing in RP4, which can be computed. We have control over that data. And essentially, when the dust settles, this argument gives us non-trivial commutators between operators realized by M2s and M5s. But this is only part of the story. This would hold in a generalized Maxwell theory. In M theory, we have more. There is a Chern-Simons term. The structure is richer and deserving of a more careful analysis. What happens if you analyze it a bit more carefully is that you find actually there is another non-trivial commutator. This time it has to do with M5 branes between themselves, which might be surprising at first. And the origin of that is actually the non-trivial flux. As you remember, this was one of the ingredients that I was sort of showcasing. And when the computation is complete, you can repackage everything nicely into these quadratic terms in 7 dimensions. The first two terms describe this abelian three-form Chern-Simons I was mentioning. That was already known by previous work. And we have essentially shown that we can also have an explicit appearance of another term related to a Z2 zero-form symmetry. And then just like in ADS 5 times S5, if you choose suitable boundary conditions, topological ones, because we want an absolute theory, for instance, Dirichlet for C3 and A1, you can get this sort of picture where now we have a dictionary between the branes and both the charged objects as well as the symmetry operators. Here, I don't expect you to follow all the details. It's sort of like a small zoo of branes. And as you can imagine, there can be other boundary conditions that can be the case. Those would be different variants, but essentially we have control over those in this language. Okay, so let's switch gears a little bit and try to say something about the diffusion structure. And here essentially I have to turn my attention to the other ingredient on the word volume of branes, namely the presence of localized gauge fields. And as we will see in an example in a few moments, essentially what happens is that because the brane contains these localized gauge fields, the sort of operators that originate from the brane usually take the form of a naive holonomy dressed with a non-trivial TQFT, which is itself coupled to some other bulk fields. And it is precisely due to this non-trivial dressing that the fusion of such operators can be more interesting than a group-like fusion. There is actually, well, there are various setups where this can be seen, but I would like to discuss this example, also because it's not really a CFT, and in that sense, it shows that these holographic ideas can also be, to some extent, used in setups that are not strictly conformal. So more precisely, I would like to revisit the classic work of Klebanov-Zeitlin, Klebanov-Strassler, and their type 2B solutions. They are very intricate and rich solutions. I don't want to discuss them in too much details. I just like to remind you that the internal space is topologically the product of an S2 and S3, and that we have some non-trivial flux, and in particular, some units of F3 flux on the 3-sphere. Famously, the field theory dual, as I mentioned, it's not a CFT, but rather this sort of quiver gauge theory that undergoes a cascade. And if we tune these parameters n over m to be integer, the IR of this cascade is believed to capture the IR of pure Yang-Mills. And from the point of view of today's talk, we only need to focus on some robust features, namely some discrete global symmetries, and those are visible actually already at the level of the cascade at every step. And they are a discrete zero-form symmetry and a discrete one-form symmetry, which also happen to have a non-trivial 't Hooft anomaly. And this has been analyzed in the field theory by various authors. And the reason why I'm selecting this example is that if you start with the SUN variant but gauge the one-form symmetry, you change the gauge group, but more interestingly, you turn the vanilla zero-form symmetry into something non-invertible. So that's sort of our target. We would like to see that from the gravity side. And according to our philosophy, we have to look at possible branes that can wrap this geometry. And it turns out that the relevant ones for this discussion are D5 branes that wrap the S3. And why are they the relevant ones? Well, one way to see it is that we can take their topological couplings and reduce them on the 3-sphere. It's not important to follow all the details, but one thing I'd like to emphasize is that we do get a non-trivial topological dressing. This is a non-trivial 3D Chern-Simons theory coupled to a bulk field G2. And as you can see, it features the gauge field that lives on the brane. And heuristically, we can think of it as coming, we know that the West-Zumino couplings are quite rich. Once we expand the exponential, we get many interesting terms. And in particular, there are terms of this sort. And if heuristically you integrate them by parts, you can sort of see, using the flux, the emergence of these couplings. And one can also do a more careful analysis, working sort of at the level of gauge invariant polynomials in the field strength. The outcome is the same. And now we can see the fusion as promised. Essentially, the observation here is that if I try to fuse this brane with its orientation reversal, which naively should be the inverse operator, I do cancel the naive pieces, but these topological dressings don't quite cancel out because each of them comes with their own gauge field. Each brane has a gauge field. And what can be done by means of an analysis that I'm not going to do for you right now is to argue that what is left is a discrete gauge theory coupled to the bulk, which can actually manipulate it to be a sum over surfaces, which is precisely a condensation defect. So here you have to sort of believe me a little bit. I'm not giving you the full argument, but essentially what we see is the emergence of something that looks like this, and it begs for a string theory interpretation, and there is one actually. What we are witnessing is a form of tachyon condensation in a d5 bar system, where essentially the top dimensional charge gets canceled, but we're left with non-trivial lower dimensional branes. And for more details, I refer to you to this nice paper of Ibu and collaborators where they actually studied this setup in great detail in this language. And as a word of caution, maybe you might be wondering, is this a non-invertible fusion always? Like, how can I recover a vanilla fusion if I so desire? And here, the thing to keep in mind are the boundary conditions. If we choose them to get the SUM theory, actually, all this sort of sum is a C number. It can be trivialized, and we get a vanilla Z2 fusion. But if we choose the other boundary conditions, we reproduce the field theory result. So if you wish, it's almost like saying that the fusion in the bulk is always non-invertible. It becomes invertible or not on the boundary, depending on the boundary conditions. And finally, in the last couple of minutes, I promise you it's mostly going to be pictures, so it shouldn't take too long. It's this idea of generalized charges. Namely, is there a stringy counterpart to that? And there is actually a natural candidate. If we sort of look at this sort of configuration, it's reminiscent of Hanani-Witten brane creation effects. Here I'd like to remind you, in a Hanani-Witten configuration, we have two different branes of different kinds that share some directions in space-time. And in the others, essentially, as you can see, they fill everything except one dimension. So they can link, just like the ones before. What makes this configuration interesting is that, essentially because of a charge conservation phenomenon, if we try to unlink these branes, a new brane is generated in the last direction, which is sort of exactly what is happening here. And so, for instance, the original Hanani-Witten setup has to do with NS5 and D5, and if we try to unlink them, a D3 will be generated. But there are many other versions of this related by various dualities. There are versions in M theory and so on. And what we can see is to actually apply them to find generalized charges in field theory. So if we revisit the Klebanov-Strasser setup, let's say we want to study the theory that has a non-invertible symmetry. It's more interesting. Essentially, this is the answer. So we have a charged line. This is the top line of this SUM mod ZM gauge theory. And then there is a zero-form symmetry operator. This is the non-invertible guy. And the Hanani-Witten transition, in this case, has to do with generating a fundamental string, which becomes a magnetic symmetry operator. So this essentially gives us a generalized charge. And finally, what we have seen in this recent paper is a similar structure in this other example I was mentioning, where, as you can see, the qualitative features are essentially the same, just what changes are the actors involved in the game, which allows us to make contact with nice recent results in the literature. Those are field theory analysis of non-invertible symmetries in this class of models, and we see their counterpart holographically. So to conclude, I've tried to convince you that the SymTFT construction is a useful tool to describe symmetry structures in field theory. And if we think holographically, branes at infinity know about various aspects of the SymTFT, and mainly the linking, the fusion, the condensation defects, and the generalized charges. There are many questions that remain open. Here are just 3 of them. One thing that I think should be nice is to get maybe a better understanding of this freezing out of non-topological modes. And another thing that I would like to understand better is we know that on the field theory side, when we say categorical symmetries, it means that there are things like morphisms, associators, all sorts of interesting and non-trivial things. Can we see them from Branes? And finally, a bit more formally maybe, can we establish a more precise connection between these categorical aspects of symmetries and, for instance, the classification of D-brane charges that we know is performed in the setup of K-theory? So can we sort of have these 2 sides dialogue in a fruitful way? And with this, I finish and I thank you.